Good afternoon, good morning, everybody. Afternoon to those on the East Coast and good morning to those on the West Coast. My name is Chris Tucker. I am a member of the San Diego chapter SCTE board. Joining me also as an organizer is Ben Johnson, president of the SCTE San Diego chapter board. And today's presenter is Stefan Meinders. Stefan is a senior product line manager at Nokia in the Deepfield business unit, whose focus is on securing service provider networks from distributed denial of service attacks. And Stefan has put together some really informative insights on today's networks and the challenges they face from DDoS attacks and other security vulnerabilities. And he's going to share with us today those insights and help us get a feel for how service providers like those in the cable industry can protect the network, their services, and all of the users that use them against those dangers. So with that, I'll turn it over to Stefan, and please chat your questions in, and we'll do our best to answer those as well. Take it away, Stefan.
Yeah. Thanks a lot. Yeah, so good morning, good afternoon from my side as well. Let's get started directly into the content. The agenda today, what I want to talk about is I would like to provide a quick introduction of our view on volumetric DDoS and how we are able to trace that. A few details on that, a bit more in section 2 there, how we identify and quantify the DDoS problem. In part 4 of this speech, I would like to talk about how to automate DDoS protection, and actually for the whole network, not just for selected users, just for everyone to protect the entire infrastructure from attacks. And then finally, on part number 4, I'm providing a brief overview of how Nokia and especially Deepfield is solving that problem for our customers. Good, so part 1, quick introduction into denial of service attacks. So there are actually two components that are most of the time attacked and that are part of our recent analysis. So things under attack is often either bandwidth or state. So attackers tend to send a lot of traffic to victims and then actually overload or overutilize the victim's connectivity. Right? And this is often done by amplification attacks. So to craft an amplification attack as an attacker, you often use something in the middle because the attacker, the guy with the intent to start the attack is often not in a position where that attacker can actually spoof source addresses of the victim, right? Because the guy with the intent to send the attack may be in a network that blocks IP spoofing. So what the attacker does then, they use something like a jump host, right? Or a service. So in most cases, it's a service. And those services are then used to craft the spoof packet from here using the source address of the victim and then sending those packets to open reflectors. And those open reflectors then respond, and the much larger response than the request here, the much larger response goes to the victim host. So these attacks, these high bandwidth attacks, are often use a combination of IP address spoofing, reflection, amplification, or flooding. And that finally then results in terabit scale attacks sometimes, right? We see lots of those attacks. Not all of them are terabit scale, but those are all kind of volumetric attacks. The attacker uses systems in the internet to send gigabits of attack traffic to the victim host. This is one part, right? The attacker's intent is to create as much traffic and send it to the victim host. Then there's another attack type, which is to compromise or overutilize the stack, the TCP stack on the victim host. That's often done or called a state exhaustion attack. It often requires also spoofing because what's done here is TCP packets are bounced off of those reflectors here. So if this attacker here sends a SYN packet here with a spoofed source address, this server here would respond with a SYN ACK, and this victim would receive many, many SYN ACKs, right? And then the TCP stack needs to handle all of these SYN ACKs. That's a problem in particular for servers, load balancers, firewalls, and these devices. So those are called state exhaustion attacks. What all of those have in common is that these attack types are provided by those DDoS for hire or DDoS as a service services available in the internet, pretty cheap to use, easy to use, and they use a combination of IP address spoofing, reflection, amplification. So we analyzed this because the interest is that 90% of all attacks are of this type. So it's actually pretty beneficial to better understand how these attacks can be created, how the ecosystem behind these DDoS attacks is looking. Looking at the DDoS threat landscape from a service provider perspective, it's interesting to know, okay, where on my network edge can those attacks actually happen? What's for sure happening is that infrastructure here gets saturated with attack traffic, right? And those attacks, reflection, amplification, flooding, that's often coming in the peering edge, and it's targeted at business customers, residential customers, and nearly everything that's available on the internet can be attacked directly. The problem is that there is a pretty high impact, and it puts SLAs at risk. Right? If you have business customers here, and you provide a managed security service or DDoS protection service to those business customers, the attacks are that large that your scrubbing capacity is overloaded, then you may not meet your SLAs anymore. And that actually could cost money. It could cost you money. For sure, a successful attack costs those business customers money, right? Because they are out of service for a while. This is more or less the case we have in each and every network. But it's not the full picture. To protect infrastructure, in our cases, infrastructure is the core network here, from attacks, we need to look at every edge. Because what we see is we have hijacked servers in data centers. Those servers are misused. So there can be east-west attacks, right? One data center is attacking another data center, or one host is attacking a host in a different data center. So it's actually traffic using your infrastructure here to be transported to the victim in trauma. So that happens also a lot. What we also see is we can have compromised hosts in our residential customer base here, right? So customers can have IoT devices that are hijacked, that are bots, right? So part of a botnet, and then orchestrated to send malicious traffic into your network, right? All of these attacks are somehow into your network. And actually, it's important to look at every edge of the network to protect the infrastructure from attacks. So how does this DDoS ecosystem look like? And how does it work? At Deepfield, we started some analysis to figure out how is it actually possible that in 2021, we still have so many attacks that require IP spoofing, but actually everyone should have implemented something like best common practices 38 and so on, right? So spoofing should actually be prevented. But it really isn't, because there are business cases behind. So we have someone here with an intent, with the idea, okay, I need to start an attack because of whatever motive. We don't know that exactly, but it's many things, right? Some examples here. So what these guys are often in networks where they can't directly send spoofed IP packets out, or it's just too complex, right? So if there is a service you could use to launch an attack against anyone in the internet, and that service is cheap, and it's actually used, right, and required, then that's the way to go. So those people, what they do, they use one of these more than 100 available so-called booter services. Now the booter services is a nice web interface, a nice web UI, where you just select the victim, then you select the type of attack, where do you want to have that attack coming from, and so on, and then it's started. But actually these things need to be hosted somewhere, right? Because then these booter applications need to be able to send out spoof packets, so or IP header modification packets. And there is another nice business case for hosting companies. So there are 50 plus hosting companies we've identified around the globe, which are offering hosting without any security measures in terms of blocking outbound spoofing packets and so on, right? So for these guys, for these hosters, it's kind of their business model to offer, you can send out, you can host, you can do whatever you want in our network. So that's their business case. And because of those services exist, we have these large amount of DDoS attacks and these very large DDoS attacks. What these guys in addition then need, because you don't want to send out the attack traffic directly from these hosting companies, right? What these guys do, they use amplification, right? So they send out packets with the spoofed IP address, the IP address of the victim, and then they send those packets to open reflectors and amplifiers. Yeah, so a small response goes here, and then that large, a small request goes here, and the larger response goes here, and your network, your customer is kind of here and then receives terabits of traffic. So there is a business case behind. That's the main point. But can we actually, if we are here or somewhere here as an ISP, can we, or as a network security company, can we track that? Can we figure out, okay, where is it coming from? What is orchestrating it? And where does it live? And that's what we try to do. We looked a little bit deeper into how do these services look like. They are actually really, really cool. Yeah. Sorry?
Hi, Stefan. Yeah, sorry. We're getting a little bit of echo here. Are you doing a Bluetooth headset, or is it speaking directly into the laptop?
Yeah, so it's just me here.
Oh, okay.
And normally it's fine. So I'm alone in my room.
Okay. It's just there was some echo.
Okay, I continue slowly. Okay.
Okay. Yeah, sorry, but didn't mean to interrupt you. It's just some folks noted that there was an echo.
Yeah. I need to know that. I can't see that. Okay, let me continue slowly.
Okay. All right. Sorry, continue.
No worries. So this is an example of one of these booter services. It's really simple to use, right? So you just provide the target IP address, the target port number you want to attack, then how long you want to have that attack going. Look, here is a maximum for the signed-in user here of 120 seconds. This is why these attacks are so short, right? Most of the attacks are pretty short because short attacks are cheap. You know, sometimes these are test attacks, which are sometimes for free. Then you select your test method, your attack method. You can select some custom features here. It also depends on your package there, right? So where do you want to have the attack coming from, right? So like geolocations, or do you want to use any or mimic any cloud services, things like that. So it's really sophisticated. How does this look like from your perspective, right? Or from carrier and service provider perspective? It a little bit depends on where you are, right? So like eyeball carriers, or carriers for residential customers here are the target of the attack. Let's say this carrier has an enterprise customer. That enterprise customer is the victim of the attack. What we did, first of all, we tracked the attack. We identified, okay, here's an attack coming in to our customer. We got an alert, for example. We identified, okay, this is the victim CIDR under attack. And then we traced it back and tried to figure out, okay, can we also see that traffic sourced from amplifiers, so we see these source amplifiers here, in transit somewhere. And how did that traffic enter transit? Right? We also look at the victim CIDR and the amplifier address. This is fine so far. The idea then is what's normally not easily traceable. Can we trace it back to the hosting company that's actually hosting this bootler service, right? And that actually lives here. You need to turn around then the source IP address because you need to look for the traffic that's going to the amplifiers, to the destination amplifiers. And as the source address victim, this is the spoof traffic, and that's what we actually did. And it allowed us to do some research on these kinds of attacks. How do they look like? What's the potential? Which bootler service actually uses which list of amplifiers, right? Because every bootler service, if they want to start a reflection amplification attack, they need to have something like a nice list that says, okay, these are all my open DNS reflectors, for example, right? And then they send packets to these reflectors, and that's typically not changing a lot, right? So we can use all of that to kind of fingerprint, hey, this attack is actually originating from this bootler service, and that bootler service is hosted at this hosting company. That's what we did. In addition, we figured out, nice little side effects. One of these side effects is we were wondering, why does our victim receive such a lot of ICMP traffic? So typically, if you think about ICMP traffic and those attacks, there is a use case from this bootler service to measure if their attack is actually successful. So could that ICMP, pings, for example, be used to check if the victim is still available or if the victim has been remote triggered black hole already or something like that. But that's truly not the case. What we are receiving here, what we see in the transit network and at our victim here, is that often those bootler services don't have very up-to-date lists. So sometimes these lists include amplifiers that are no longer amplifiers, that have been patched, right? And those amplifiers, if they then receive that traffic, they would respond with the ICMP port unreachable, for example, or things like that. And those responses never go back here, right? Because the address was spoofed. So the responses also go to this victim under attack. So what actually happens very often if you are under a bootler service attack is you get a lot of traffic from the misused protocol, DNS traffic or NTP traffic, CLDAP, and so on. The list is really long. You get a lot of fragments, right? Because fragments are a result of that large amplification factors you often have, and you get ICMP traffic. If you use all of this in combination, you can do pretty good identification of where is that attack actually coming from, what is this service. And that provides pretty good insights and pretty good information on, okay, what can we do to tackle these attacks and what could be an idea. So if we look at DDoS in 2021, so we've seen an increase of nearly 100% of the total amount of DDoS traffic. And in a little bit more than a year. So the daily peaks of DDoS traffic, all DDoS traffic combined, were rising from 1.5 to nearly 3 terabits per second. Why is that happening? That's mainly because the number of amplifiers is growing quickly. That does not mean, okay, we have more open DNS resolvers, or we have more vulnerable NTP, or something like that. It's actually the attackers, the GUI service providers, and so on. They figure out more and more different protocols that can be used to reflect and amplify attacks. So the attacks are just getting more and more diverse. Another reason is the number of botnets is also growing quickly. The next reason is those services are just used more often because they are so easy to use and so cheap. So another thing is, again, the ecosystem, the financials behind, right? Yeah, one of the incentives for attackers is something like ransom DDoS attacks. Right? This happens over and over again, that customers are receiving emails and say, we will DDoS you. Here's a test DDoS 200 gigs. You will receive a terabit if you don't pay X in Bitcoin. That's what's happening. What is a little bit scary from our analysis of which lists are these attackers using, because their current lists are so outdated. If they would have a much better list, there is a potential for much larger attacks. So we believe it can be 4 to 5 times larger than what we've seen today easily by having better lists. If we compare it to our own lists, right, because we create reflector lists as well, right, because we want to know them, we want to use them in our product, and our lists are pretty accurate. And if we would use our list, we would be able to create much larger attacks. That's the point. A little bit of a good news here is there are something like 50 hosting companies and regional providers where those attacks really originate from, right? So those hosting companies that host the DDoS for hire service. Our main issue today with these DDoS attacks is that there is a large misbalance between the cost to start the attack and the cost to protect or to mitigate the attack. And that's an economic challenge. And we try to fix that problem. Good, so are there other approaches? There are flow approaches to stop DDoS and make that problem go away. So it has been tried to fix amplifiers and patch botnets. That's actually kind of a lost case because there are just so many protocols vulnerable. People will figure out other protocols to be used. In some cases, those amplifiers are configured on purpose, right? Some attackers hijack servers and then they start NTP services there, CLDEP services, and so on. Right? So if you see multiple of these services originate from one IP, right? So there's an IP address that runs an NTP server, a CLDEP server, a DNS server, and a few others, then you're pretty sure, okay, that thing is compromised and is a reflector actually on purpose. So that's kind of a lost case. That's not really doable. Commercial booter takedowns, that does also only kind of work, so it's not that effective because otherwise we wouldn't have the problem anymore. Right? Deploy specialized DDoS hardware, yeah, indeed, that works, but that's expensive, right? So and Moore's law is an issue there. So doubling the mitigation capacity every year is just too expensive. That's not going to work. So there are a few things that are a little bit better to come around these DDoS problem. One, of course, for large service providers and services is they move into CDNs or into the cloud. That often, of course, helps because those CDNs and cloud services do provide pretty well DDoS mitigation services and so on, and they can just absorb the attack. What was pretty good as well is use the community. that would work, right? So as more ISPs are configuring their network and manage their network according to best common practices 38 and so on, and to block actually spoofing at the edge directly, that indeed helps as well. What we believe is the best solution and one of the most cost-effective solutions today is use actually advanced and high-performance routers to block DDoS attacks directly at the network edge. And that's much cheaper. So our Bell Labs colleagues created a nice business case and compared it, and it's actually nearly 85% cheaper compared to the present mode of operation that's mainly using scrubbing devices. So it's a good idea to do that directly on routers. Excuse me. So a decade ago, that was not really doable. Nobody really trusted a router to a peering router, right, to have tens of thousands of access lists active. There were not really good telemetry protocols. SNMP, yes, but that has, let's say, something like you query your routers with SNMP every 5 minutes, so you don't really get real-time telemetry, right? And if the attack is just 5 minutes short, that doesn't really help. So routers were just not built at that point in time to be a very good device to block DDoS attacks. That has changed today. So today, routers provide extensive telemetry capabilities. IPFix and gRPC are pretty helpful there. There's a significant increase in the number of filter entries and in line rate capacity. So all major routers support FlowSpec and NetConf today. So providers actually today have more trust into putting some automation around access lists, like using FlowSpec, like using NetConf to dynamically configure these routers. And we can do that in a pretty safe way. So network security and network engineering, they share the infrastructure today. So before that, we had dedicated resources for security, now firewalls and those things, and we had dedicated routers. Today, those two types of devices are more merging. So we have security features available on routers today, and the network security and engineering teams are more collaborating on fixing the problem. So automating DDoS, mitigation on network edge routers, that's really a new mitigation scenario. Because so what we have today, right? So, and Deepfield Defender, for example, is one example to orchestrate, to manage those mitigations on routers. So we receive flow data from the network, meaning BGP, other telemetry information, analyze it, compare it to our data feed, identify there's a DDoS attack, and then we want to do something against the DDoS attack, right? So one thing that's always available and has been available for 30 years is remote trigger black coding. But that completes the attack, right? The victim is completely unavailable anymore. That does not work, right? If we see attacks these days that are not just having one target IP, right? If that one target IP would be a subscriber, you could say, okay, I black hole that subscriber, I provide a new IP address to that subscriber, and then we are good, right? But as soon as those are static IP addresses, businesses, or as soon as I have my entire subscriber base under attack, if the attacker is just going through all IP addresses in my IP pool I allocate to subscribers, then I have a problem with remote trigger black hole easily. I run into the same problem with my scrubbing center, right? So most of the time, my scrubbing center is dedicated to my, let's call them VIP customers or enterprise customers that in many cases pay for protection services, right? So those are dedicated there. I can't really use that to protect my residential subscriber base in addition because I easily might have thousands of subscribers under attack. And then running multiple of those mitigations is an issue here from a scalability perspective using scrubbing centers. So to tackle that a little bit, FlowSpec was used a lot. FlowSpec was mainly used to kind of tackle this overload situation here on scrubbing centers a little bit. Right? It's always the question, okay, if I run out of scrubbing capacity, what do I do? And then the answer often was FlowSpec. Okay, FlowSpec often was a manual approach, like shown initially, right? Frequent attacks sometimes last just 5 minutes. And then I have thousands of IPs under attack. That does not work. Manual approach using FlowSpec doesn't work. If FlowSpec is used, then it needs to be completely automatic. And in automation, in fully automation mode, FlowSpec is a tricky thing there. And in addition, it's quite limited. We will get to that later. So what can we do? What can we do better? Is there a new mitigation option that is already in the network? And that's the case today, right? That's using mitigation options, filter entries directly on routers. In best case, implemented via netcom. So that's what my talk today is about. That's my my solution to stop DDoS attacks against infrastructure, against anything that's connected to the network. So why do we need this new approach to block attacks? The attacks are too easy to launch, too cheap, and so on, right? So we talked about these booters, DDoS as a service-based attacks, cheap, high volume, very damaging, short but high frequency. So what we need, if we build a solution, we need a low time to detect, right? Detect it immediately and immediately start a mitigation. There is no way, if you identify there's an attack, then the system needs to start something like a refine process and then figuring out with whatever learning, machine learning, artificial intelligence, whatever, figuring out, okay, this is actually the attack pattern, and then mitigate it. That's in most cases by far too slow. It of course requires full automation because any manual intervention here makes it too slow. Another thing I would recommend is use fast flow, right? Reduce your flow export timeouts to the minimum that's supported, or use uncached net flow. To export the flow information immediately to the collector and to the detection engine there. So we need a new approach because we have a lot of reflector and protocol variants. There are many new applications, protocols misused for amplification. And it's not just DNS, NTP, CLDOT. Even if we see those most, right? But just blocking these reduces the amount of DDoS traffic you will see, but that's not enough. There will still be gigs of MDNS traffic, for example, of memcached, right? So in addition to those, so this here is a list of reflection amplification attacks. In addition, I mentioned it here as well, we have these very nasty TCP reflection attacks. If we have time, I can explain that a little bit more, why it's so tricky. It will come up a few times more in this presentation. So as soon as we have a system where we need to provision it, now where we need to say, okay, this is my destination I want to protect, and these are the different protocols here I want to look for, and then I need to provide a threshold per protocol. In that case, that's a lost game, right? Because the thresholds need to be changed. They need to be tuned over time. If you baseline them, the baselines are often too much off. And as soon as the system needs to compare those things, there is too much time that goes by, right? So how long does the traffic need to be above baseline before, or above threshold before an alert is created, for example? So that's actually not really good. So what we need, we need a feed-based detection and mitigation rule set. And that must be not hard-coded in the system. So in that case, the security solution operator provides what we call a DDoS classification feed. And that provides real-time detection in combination with telemetry data from your edges, input and or output. So real-time detection in this case means there is the flow data. As soon as it arrives the system, the flow gets classified, and the system is not waiting for seeing many of those flows, whatever. It classifies a flow immediately as suspicious or not. And a single flow can be suspicious. That does not make a DDoS, right? But if I see many of suspicious flows to one destination address, for example, then create an event. That's the idea behind. So immediately detect something's wrong. And also show there is suspicious traffic on links even without creating events. Right? So if you are just interested from an analytics perspective, hey, would it be possible to show me how much DDoS traffic is on this peering link? Right? You cannot set up everything as a monitored object or something like that, and then look through monitored objects. Yeah? Get the visibility into all traffic that's flowing through the network. So in addition to that, from what could we potentially do? So first of all, if we identify all of these reflectors, couldn't we just block all these reflectors from sending traffic? Sadly, that does not work, right? Because of the number of different protocols to use to be exploited, and the number of open servers, it would require millions of filter entries. There are millions of open reflectors today. So multi-vectors here of different types. Right? If we sum up all of those, then it's just too much. Sometimes even CDN sources, CDN source siders are included. We can't just block them. And if this then that flow spec approach does also not work, right? So it's easy to miss the attack and then have a lag of predefined flow spec definition. So the system should not have something like, okay, if this is my attack vector, then start exactly this flow spec announcement. Yeah, so that also would not work. So what we need is a feed-based detection and mitigation on packet attributes in addition. Look for packet length, look for TTL values, look for TCP flags, and those things. And the system requires a peacetime traffic data model to build allow lists in real time instead of block lists. Right? Block lists don't work. And those lists need to be per destination, so kind of multi-dimensional in addition, so per protocol, location, peers, and so on. Combine all of this to create a very granular trusted source list that includes CDNs, trusted services, and so on. So that's required, and that's often coming from the analytics engine of such a DDoS identification product. So using this is actually pretty safe, even if someone is using Google as a reflector, for example, to reflect TCP SYNs as TCP SYNX, right? Because even in that case, it's doable to identify the attack by looking at, okay, where does my victim under attack normally talk to in Google, right? Google is large, right? But from a victim's perspective, Google is actually pretty small. You are talking only to a number of known CIDRs in Google. And they vary, of course, per region, location, and so on, right? But they are actually pretty small, so it's doable to allow list those things and then rate limit everything else. And even if under a large attack, having the main services the victim is mostly talking to available is already a huge benefit compared to completely under DDoS and go offline, right? So I think that's required. The next thing is we have two diverse targets and victims. Every internet routed IP can be attacked. And every internet routed IP is more or less important. Yeah? So let's say 2 years ago, we really said, okay, for residential subscribers, okay, we can do something. We can get them quickly online again by maybe blackholing their traffic, reconnect them, get them a new IP address, everything is good again, right? But today, we have business traffic at nearly every home because many people are working from home, right? And then, disrupting homework, their work from home, that's of course, same like students learning from home and so on. And gamers are often unhappy if they are under attack, right? So we need to do something to support mitigations for those things as well. We also have IoT devices that we want to protect. So IoT devices, of course, they are not just a DDoS problem, right? So they are also getting attacked. And sometimes those IoT devices, if they are constantly under attack, they are entirely damaged, right? Because their battery that was built for, okay, it lasts 10 years or something like that, it's completely drained because of the DDoS attack. And then after, whatever, 3 months, that thing is unusable. So there are large problems in nearly every network. So we need to do something to protect everything. Selective protection, therefore, selective protection is not sufficient. Right? And in addition, thresholds, baselines, they won't work for detection. So we need to be aware of also of collateral damage. There may be, the attack may be to a victim that sounds pretty unimportant to us, but it's not the intent to really attack this victim. It's the intent to create as much collateral damage in the network as possible. Sometimes we don't know why a target is under attack, and that's not important at this point. And then we have another problem, which is the corporate bomb and bits and pieces attacks, right? That smoke screen things. So where just everything in our customers' networks is under attack, and you don't really know why. The only thing you know is if everything is under attack, I cannot divert that traffic to my scrubbers anymore because in nearly all cases, there's not an equivalent of scrubbing to clearing capacity available. So that's an issue. So for DDoS protection, for services there, it does not really apply, right? This does not apply. So if you provide DDoS protection services to end customers, to enterprises, and so on, you would still do your diversion and use the scrubber and so on, right? But your SLA is at risk as soon as your scrubber runs out of capacity. The next thing, which is important for a new system and a new mitigation approach, is we need to look for false positives and false negatives because that will break automation. If I constantly have false positives, I will constantly start new mitigations that were not required, or if I have false negatives, I will miss the attack and not start any mitigation. So we need to have a pretty good, precise detection. What often really goes wrong is if something needs to happen, then that's called feature extraction. So the system analyzes the attack and then figures out, okay, this is the attack protocol, this is the whatever average packet length, and this is this, and so on. And then it starts to build on demand a flow spec announcement and sends that out to the network. That's pretty error-prone, and it's non-deterministic. And often it does not respect router capabilities. Right? What if that thing creates something that the router doesn't support, or that's above limits on that router? So we need to have a system that has a knowledge of capabilities and limits of the routing devices it does orchestrate and instrument. In addition to that, we need to monitor in real time the mitigation feedback from these routers. How many packets are currently blocked? How many packets are forwarded? How many packets are matching on our echoes and so on? And that, in best case, in real time, right? So if I say real time here, I mostly mean something like 5 to 20 second update intervals, pretty short intervals. This problem, I touched that briefly already at the beginning, right? We need to look at multiple input edges. We need to leverage existing but enhanced network telemetry information. So IP flow is pretty good. Many router vendors increased their support for flow exporting. You can have better sampling rates. You can export much more often, and so on. IPFix supports additional fields to get us knowledge around TTL, for example. We need to have BGP information and SNMP information to actually get an understanding of the topology of the network. So using all of that and combine it creates a pretty good picture of the network. Then we need to monitor all edges inbound to the core network. So peering edge, attacks coming in from external to my peering. And I also consider on the service edge, so on the access edge, attacks coming from my customer into my network as an inbound attack, right? It's coming from my customer into my network. So from my perspective, I'm looking at everything from the service provider perspective. All edges and a diversion-based approach that is really, really hard to implement, and it would not scale, and it's extremely expensive. So that's not really a valid solution. This finally, after these initial points, gets us to the point, okay, router-based inline mitigation. The router sits always inline because it has to see the packet because it routes the packet. So if that thing could also inspect that packet, that would be great, right? So that's, from my perspective, that's the way to go. So good, we can have scrubbing centers dedicated to enterprise customers. This is an existing and required for higher level attack mitigation to protect my managed security service provider customers. Of course, it's dedicated because of scale limits, right? I know a scrubber can do 50 concurrent mitigations, and then I know, okay, if I have 50 customers under attack at the same time, I run 50 mitigations. For enterprise customers, that works. It's pretty predictable. That's fine, right? If I want to protect my residential subscriber base, I may have 200,000 subscribers. I may have 20 million subscribers. That's above my scale limits for sure. Good. But what these scrubbing centers have, they actually have something that's called countermeasures. And countermeasures are predefined mitigation methods, how to block the attack. And they have countermeasures for volumetric attacks. So what do we need to do? We need to take these features here and replace them by features that are router-based. So we created router-based countermeasures, and those router-based countermeasures would then filter the attack also for my scrubbing centers. So even before the traffic reaches my scrubbing center, it has already been filtered, so the volumetric piece of the attack is already gone on my network edge. That's the idea. So finally, I'm having more capacity for my remaining attack vectors, which may be amplification, not amplification, but application layer attacks, for example, or other state exhaustion attacks, or attacks, encrypted things. So I have more capacity. My scrubbers do what they are really good at, but my volumetric attacks are now router-based inline mitigations. So I'm making an optimized use of my scrubbers. Yeah, last but not least, the advantages here. If I do router-based mitigation, right, I get high throughput and scale. It's inline. There is no latency. The packet needs to go through this router anyway. There is no diversion. We leverage existing, I say modern routers here. We can do that easily on all edges, and it's part of the infrastructure itself. And that finally is rebalancing the attack versus mitigation cost. Right? In that case, if all of this, what we see down here now, fully automated, works, there's a pretty good cost balance then from the attack to the mitigation part. Good. So yeah, a recap real quick. There is a large potential for attacks in the future. So 10 terabits or more. That's 5 times bigger than today, what we've seen today. Most DDoS traffic originates from, let's say, just 50 hosting providers, but it's hard to what would you say if you take down those 50 hosting providers, right? That's also not doable. There's too much money in the game. They will show up somewhere else. The guys will just recreate them somewhere. I think that will not work over time. So good news is we have advanced high-performance routers like Nokia before service routers, and that can mitigate volumetric attacks and have a significant cost saving because I don't need to grow my scrubbing center from, let's say, 200 gigs to a terabit or something like that. And finally, automation is essential for the next generation of DDoS protection, right? Because there is no chance to get that done manually. Good. Yeah, of course, we are Nokia, so we've built a solution to do that. And this is a summary of key requirements. Right? We went through my key requirements I see that are necessary to build a service that really can tackle these attacks. For us, this is a summary of our key requirements we've been used to build our solution around it. It has really good peacetime traffic modeling. The DDoS detection is pretty accurate. We do infrastructure protection, detailed reporting. We can provide security as a service by providing portal access. We do everything fully automatic. And if someone wants to manually, let's say, make an automatic mitigation better, there are also workflows to support that and so on. So it's easy to control. That's the main thing. Yeah, everything that's required actually to make this happen is a little bit living on our genome technology. So our genome technology, it actually scans the internet and then it identifies hosts in the internet as either good or bad, right? All good things like cloud services and sites and services, traffic. We put traffic categories in here. So Cloud Genome has information about all that good traffic that normally is there from services provided to subscribers, for example. The other side of that is monitored by our Deepfield Secure Genome. So we scan the internet, we create our list of DDoS reflectors. So we know traffic's coming from a reflector. We know this is a reflection and amplification attack if traffic's coming from there. In Secure Genome, we provide then DDoS classification and detection rule sets, and we do also provide the countermeasures. So in Nokia Deepfield, you get everything you need to identify the attack, automate it, and mitigate the attack. That's the key message here. Good. So the entire solution actually starts with Deepfield Defender here that does detection. We also do DDoS analytics and automation. Then to do that, we need to receive information from the monitored network here, the IP network, that's flow, BGP, SNMP, and telemetry information. We send out mitigations. There's a better picture with a bit more detail than this, like here, right? So Secure Genome is a data feed our customers get. They use it we control the network, we get feedback from the network, and we provide a UI and an API to our customers to use Deepfield.
Hey, Stefan, can I jump in? Just want to make sure there's enough time to answer questions.
Yes.
Again, thank you, Stefan, for this presentation. Obviously, very interesting, and it's a little over my head. I'm just a fiber guy, but it's very, it's obviously going to be more and more important. We see on the news various cyber attacks, especially against military companies that subcontract or work with military contractors. So I'm sure this will become ever more present in our lives on a commercial level. So with that being said, if anyone has any questions, if they could please insert them into the question box or send it into the chat. We'll stay on for maybe, would you mind staying on for 2 more minutes, Stefan? Would that be okay? Just so I can see if there are any questions in the box.
Yeah, no worries.
Okay, so we'll stay on for another 2 minutes or so, and then we will look to conclude the presentation. Any things that you're looking out for in the future of technology and DDoS, Stefan?
Yeah, so from a deployment perspective, right? So Deepfield currently has 60 plus customers, and we have 10 plus customers running Deepfield Defender already in all regions. So it's pretty interesting to see what's going on, what our customers are attacking, how they're using the product. So for me as a product line manager, that's really a great point in time, right? So seeing everything that we've been building over the last year and seeing it in action, how it works, and so on. So I'm really looking forward to that. And from a DDoS perspective, right? So it's year over year there is a new record attack. Year over year, there are reports that the number of attacks are increasing and so on. So it's just getting more and more and more important. With the entire innovation in the industry, right, I even think it will become even more important. So because there are just more services relying on the internet, right? The entire what we call here Industry 4.0. So the industry automation and all that stuff, security is a must-have, right? And DDoS is required.
Yeah, they've even changed some of the NIST certifications. Now companies in the U.S. need to do third-party certification on their security infrastructure. If you're looking to again, I'm tying it back into military, but I think it does tie to operators potentially in the future that the folks that they work with there'll be maybe some sort of trail of meeting certain standards handling their technology or how they manufacture their devices and components. So it'll be interesting to see. It'll be interesting to see. As you mentioned, to do the attacking, it's not so expensive, or certainly less expensive than protecting against the attack and resolving an attack that is has been completed or is ongoing on your network. Or so it's we'll see what happens. But I don't see any. I don't see any questions. So. Okay, we'll look to conclude this, and thank you everyone for joining. If you would like to see any other presentations and you are a member of SCTE, you can go onto the website. There is a long log of presentations that you can use to learn more about DDoS or about different sorts of network infrastructure or end-face cleaning for fiber optics and all sorts of, it's a great resource. So, and if you are looking to get more involved in SCTE, please reach out to us, and we have some really exciting events coming up, so we hope that you can participate. Anyway, Stefan, thank you so much, and I will end this presentation if it's okay with you.
Yeah. Thanks a lot.
All right. Thank you.
Bye.
Bye. Have a good night.
Good night.